Thank you so much, Reiko, and thank you to the organizers also for inviting me. This is my first Evolang, and I have to say it's by far the most interdisciplinary conference I've ever been to. It's quite extraordinary. It's also that fact of this interdisciplinarity that makes me extremely nervous about giving this talk. So that might be too loud. Can you guys hear me in the back? I know there have been some auditory problems today. All right, so the question of what's special about different aspects, different domains of human behavior has been around for a very, very long time. And while the cover art has changed over the decades, the general issues have largely remained the same. And about what is special about different aspects of the mind and about language in particular. In my talk today, what I'd like to try to do is to describe my research and other people's research on infant learning, about the mechanisms of infant learning. And I'm going to try to suggest that studying infant learning can provide us with a bridge between specificity and generality, can provide us with some hopefully new and possibly useful to you ways of thinking about what's special about language and what might not be so special about language. So here's an overview of my talk. I'm going to overview a lot of studies and give you almost no information about most of them. All the work I'm going to talk about today is published, but hopefully during the wine or the excursion or something, you can corner me if you have questions about details of a particular study. What I'm going to try to do is this. I'm going to suggest to you that infants possess powerful learning mechanisms. I think this is actually now remarkably no longer controversial, which makes me very happy because this used to be a fairly controversial statement, but I'll still provide some evidence. Then I'm going to suggest that these mechanisms are both domain general in terms of their computations, but also domain specific in the ways that they interact with input domains and the output of learning. I'm going to further suggest that the kinds of patterns that infants find easier to learn may have influenced or may be related in some way to the types of patterns we observe in the languages of the world. And finally, I'll return to the question of, given all this apparent quasi-generality, some speculations about what might make language learning and language learners still quite special. So let me begin with learning. We all sort of take learning for granted, I think, because it's ubiquitous. And I'm going to try to dissect learning a little bit in this talk. So my own work has been largely focused on learning mechanisms. What are the means by which infants or other learners extract structure from the environment? But I want to point out at the outset of this talk that we often forget about two other really important aspects of learning, namely the input to the learning process and the output of that learning process. And during my presentation, I'll come back to this point to suggest that when we consider not just the mechanisms in isolation, but how the input is perceived and represented and how the output is perceived and represented, we come to a more nuanced view of how learning unfolds. All right. So let me begin with one type of learning that, as Reiko said, I've been studying for a rather long time, and that, again, at this point is relatively uncontroversial, but I'm going to introduce you to it regardless because some of you might not be familiar with these ideas. One aspect of learning that seems possibly to be quite useful to infants is the ability to track patterns of tokens, patterns of events or elements in the input. This is often termed statistical learning. I consider it to be just one form of statistical learning, as you'll see from throughout this talk. But in my own work, I first started thinking about this idea when thinking about how babies break into language. Because when we speak to infants, we don't talk like this. There are no little pauses between words and speech, even speech to babies. And my own personal experience in Kyoto certainly bears this out. There is this sort of babble of language flowing all over me, and occasionally I'll pick out, hi, or some other word from the Japanese flowing over me. But for the most part, I have absolutely no idea not only what people are saying, but where the words lie. And in my work in graduate school with Dick Aslin and Alyssa Newport, we explored the hypothesis that part of how infants might figure out where words begin and end in their native language, a necessary precursor to acquiring anything more interesting about language, like what words mean or how words combine into syntax, how words fall into lexical categories, syntactic categories, you first have to find which sounds are words. And we hypothesized that one way that infants might do this is by tracking the probability of co-occurrence of syllables in the speech that they hear. So to use a now quite overused example, if you take the two-word sequence in English, pretty baby, how is an infant to know where the words are? That could be just one long word. It could be three words, pretty baby. It could be two words, pretty baby, and so on and so forth. How are infants to figure out that pretty is a word and tibe is not a word? And it turns out that if you compute the statistical probabilities with which, for example, pr is followed by t, or t is followed by be, or indeed how often t is preceded by pr, this works in both directions, that you won't get it right all the time, but the probabilities point you towards word boundaries. So more often than not, two syllables that predict each other reasonably well are going to fall inside a word. Two syllables that don't predict each other reasonably well, like tibe in this example, are going to span word boundaries. And in studies, in our original work, we tested this hypothesis by playing babies languages that sound like this. Fascinating stuff, where we built particular probabilities into the speech. In more recent studies, we play babies something like this. The Italian speakers in here might notice that that is grammatical but slightly semantically weird speech. The idea here is that what we're exposing infants to is continuous speech that contains no cues to word boundaries other than the statistics that we've built into the speech. And we're going to ask whether infants can discriminate between sequences of higher probability versus sequences of lower probability. And I'm just going to walk you through this example from our 1996 paper just to make sure we're all on the same page. So here's the sort of thing the baby might hear. So they're going to hear something like this. The structure of these materials is something like this. And the question of interest is whether infants, after listening to something like this for 2 minutes, can discriminate. These are 8-month-olds in the original work. These have now been pushed down to newborns in other people's labs. Whether infants can discriminate between something like the quote-unquote word tokibu. This is a word only in the formal sense that these syllables follow one another with some regularity. It has no meaning to anyone but me. I'm the only native speaker of this particular language. We ask whether they can discriminate something like tokibu, where to is followed by ki with 100% probability, and so on, from what we'll call a part word, a sequence spanning a word boundary like bu, gi, ko. In this corpus, bu is only followed by ki 1/3 of the time, so there's a dip in the probability at that point. And we're going to ask whether babies can discriminate between sequences like tokibu, which are words in this speech, and sequences like bugi ko, which is sort of like tibe in the pretty baby example. Now, how do we ask this of babies? Most of the studies I'm going to talk about today use a very standard method called the head-turn preference procedure. For those of you who don't hang out in baby labs, I'm going to walk you through it just so you believe me that we can get reliable behavior out of infants. The idea behind this method is that we're going to exploit the infant's interest in different test items as a function of what they've learned during training. So for the first 2 minutes of this particular experiment, the baby's sitting on her parent's lap, and she's listening to toki bu bugi ko babu pu toki bu go la bu. It's very scintillating. After 2 minutes, she'll have heard go la bu 45 or 90 times, depending on the experiment. She'll get a little bit bored. Then the room goes silent, and we have little lights mounted on either side of the wall near the baby. Back in these days, it was lights. Now it's computer monitors. And there's also a light in front of the baby that we use to get the baby's attention between trials so that we know when we start a trial that they're not like trying to eat their sock or grab the headphones off mom or whatever. So at the beginning of a trial, a light will start blinking on one side of the room, and the experimenter who's outside the room will hit a go button. And when the baby looks at the light, The experimenter hits the go button. And the computer monitor on that side of the room will start to repeat one of our test items. So the baby will hear something like, toki-boo, toki-boo, toki-boo. And it keeps going as long as the baby orients towards that light. When the baby looks away, the baby has 2 seconds within which to look back. If the baby stays looking away, then the next trial starts with the central blinking light. So let me just show you a little video clip of this. It's an old video clip. You can tell from the way the computer monitors look. And it's going to wend in kind of a drunken way. But it'll get close, and I'll be able to narrate once we get a better image of the baby. Okay, center light, side light. And it's done. Center light, side light. He's done. And the study moves on. Okay. So using this method, we've been able to show that with a variety of language stimuli, infants are able to discriminate after just a couple of minutes between sequences with better internal statistics versus sequences that have weaker internal statistics, either spanning a word boundary or actual words from the speech that have lower internal probabilities. But babies can do more than track these tokens. They can do more than remember particular syllable combinations. They can also learn patterns of types. This is what is more typically called rule learning in the literature. I'm going to refer to it in this talk as learning patterns of types. And the idea here, I'm sure many of you are familiar with it. In fact, this kind of task has already shown up at the conference. In Gary Marcus's original study, babies were trained up on sequences of syllable triads where the particular identity of the syllables changes from one sequence to the next. So they might hear ga-ti ga, wo-fe wo, li-pa-li, something like that. What remains constant is the pattern of types, that the A's, the same syllables, are on the outsides and there's a different syllable in the middle. The tokens change on each presentation. And the really interesting thing about this aspect of learning is that here babies are able to generalize beyond the specific tokens that they've heard. So they're able to recognize novel sequences that follow the same type pattern. In this case, that follow, say, the same different same pattern or the same different different pattern. So they're generalizing beyond the tokens and recognizing the types. So there's been a lot of interest in whether these learning mechanisms are just for language, just for speech, or are they available for learning in different domains, right? It's a very basic kind of question to ask. Are these learning mechanisms solely for language, or are they available more generally for learning in other domains? The answer is that they are not specific for language, but note my little asterisks and that I'm going to say there'll be caveats forthcoming. Those of you who know this literature well know that I'm glossing over a lot of stuff here. But the general pattern of results is that infants seem to be able to track tokens and or types across a lot of different types of input. So here's one example where infants are tracking tokens. So that sequence of sine wave tones has the same statistical structure as go, la, bu, pa, bi, ku, tu, ti, bu, except now the statistics are written between C sharp and D and F sharp instead of between go and la and bu. Infants are also able to track tokens and types in sequences, visual sequences of various kinds, and moreover, these learning abilities seem to be available to non-humans as well, at least to cotton-top tamarins and rats, both of whom seem to be able to track sequences at both the token level, remembering the specific exemplars, the statistics as particular exemplars, and the type level, abstracting patterns like ABA or ABB. So if I were to stop here, the answer would seem to be fairly straightforward. It would say, okay, these are general learning mechanisms, they seem to be available at least to some other species, and so they're not really for language in any particular kind of way. But I don't think that's the whole story. I think the story is actually a lot more interesting than just saying that these are general purpose, flat earth, empiricist kinds of learning mechanisms. And the reason why has to do, again, with thinking about not just the mechanisms themselves, but how they interact with the input to learning, which comes from particular domains, and how they interact with and what kind of output they provide, which gets dumped into different domains. And to make my point, I'm just going to give you a few examples of some of the subtleties of the circumstances under which infants seem to be able to track types and/or tokens, to suggest to you that the story is a lot more interesting and subtle than just babies can always do it or they can never do it. So I'm going to have to go through these examples with some rapidity, but again, these are all published papers. So one kind of cool study was done by Colin Dawson and Luann Gherkin to do with the type learning, the quote-unquote rule learning in the musical domain. They played babies sequences of chords, and they found something that at first blush is kind of surprising. They found that 4-month-olds could do it. They could track the ABA types of patterns in chords, but 7-month-olds couldn't, which is sort of the opposite of the kind of pattern you'd usually expect to see developmentally. But their explanation makes sense. What they argue is that over the second half of the first year, we know from the music perception literature that babies are developing a sense of tonality. And they argue that for the 7-month-olds, their sense of tonality, of musical tonality, of Western musical structure in this case, is actually interfering with their ability to learn and abstract these sequences in a way that the 4-month-olds are not messed up. Another example has to do with the structure of the information itself. So in a recent paper by Eric Thiessen, what he argues is that in both the linguistic and the non-linguistic domain, redundant cues seem to really help. He is able to show that in the non-linguistic domain, if you add redundancy, more than one cue that's correlated, infants are able to track the ABA types of patterns. But that ability goes away if you strip away some of the redundant cues. And he finds the exact same thing for linguistic stimuli. If you strip away some of the redundancy across the syllables, the redundant cues to the ABA structure, then babies fail even in the linguistic materials. So the structure of the input really matters. And a related point has to do with the way babies perceive the input in the first place. Is my sound going in and out? Is it annoying? Do I have to do something, like have them fix it? Okay. Just raise your hand if it gets annoying. I'll call on you. So in order to learn, a learner must be able to perceive the input to learning. You can't track the statistics of something that you can't perceive. And so we did a number of studies in the music domain where we can actually manipulate certain features of the input more easily, showing that depending on how learners perceive the input, they learn something different. So if you take a sequence of tones like the one I played you before, that thing, you can actually track two different types of sequential statistics in there. You can track how often F sharp is followed by C sharp, which is what I said earlier, but you can also track how often an ascending perfect fourth is followed by a descending minor third. You could track the relative pitch information. It turns out that when we played a corpus of tones to adults and babies, they learned totally different things. It turned out that the adults tracked the relative pitches. The adults were tracking the probability that an ascending perfect fourth was followed by a descending minor third, but the babies were tracking absolute pitches. They were tracking the probability that A is followed by C sharp is followed by B flat. So because they had different perceptual primitives going into this, then they found they might have used the same statistical learning mechanism, but they learned something totally different. And we found in subsequent studies that if we changed the structure of the input, we could flip around what babies were tracking. So for the adults who like to track the intervals, we found that if we made our materials more tonal, any of you who are music people will understand this better than others, I apologize. The original materials were atonal in the sense that they didn't have a tonal center. Each pitch occurred equally often. When we rewrote our musical corpus to be in C major, we got the adults to track absolute pitches. And similarly with the babies, when we rewrote our corpus so that it was continually transposed, every word meaning three-tone sequence, every time it happened was transposed into a different key, we could push the babies into tracking the relative pitches because the absolute pitches were no longer informative. This is actually following earlier work in birds. And so depending on what the infants were perceiving, what the units of perception were, they learned something totally different from the corpora that we played for them. A similar kind of point comes from some work that we did on tracking at the type level, so in the ABA, ABB types of studies. It can be difficult to get infants to track these in certain non-linguistic domains. And we've reasoned that one reason that babies might find this certain domains difficult for tracking types is if you have sequences of different ABAs. Let's imagine that you're seeing different shapes on each trial. The babies have to be able to figure out that all of those triples are actually part of the same category in order to extend the category to novel exemplars. Speech is like that. We know that babies can extend if they hear li, fa, li, wo, ti, wo, and then they hear mi, pa, mi. They know that those are all part of the same category. But they might not know that green triangles and red circles are part of the same category. And so we ran a version of the study using pictures of dogs or pictures of cats. And we're able to show that when we provided infants with input where they could readily categorize it as part of a single domain, they were able to generalize. The last example I want to give you about the subtleties of this process is an incredibly clever study done by Luann Gherkin. She was interested in this study in how the input pushes learners around to affect what level they learn at. And so she gave babies a task like the original Gary Marcus, we, fo, we, la, ti, la kind of task. And she found the same kind of learning that they had originally found, that babies generalized to novel materials. Then she changed it really subtly so that one of the syllables was always the same. I can't remember what it was. I think it was T or something like that. So each triple started with T. Or, to be honest, I don't remember exactly which syllable she manipulated. But what she did was, by guiding the infant's attention to something that wasn't changing in the stimuli, she led them not to generalize in the same way. So they no longer generalize an ABA type of pattern. They generalize something like a TBA type of pattern. So by the broader point here is that the structure of the input, both in terms of how it's structured and how infants perceive that structure, can radically change what infants learn. So learners' representations of the input are going to determine what they're going to learn. If the input is structured like language, they're going to learn something more like language, even if it's the same learning mechanisms. So I think it's a bit of a conceptual fallacy to even talk about general learning mechanisms when the structures of the domains and the perceptual abilities that track those domains are so very different from one another. Okay. So this brings me to the third point, the third piece of the talk, which is the learnability piece of the talk. And what I'm going to talk about now is the idea that is shared by others as well, that part of why languages show certain similarities across the world has to do with similarities of infant learning mechanisms. That is, the hypothesis that it's possible that the kinds of things that infants are good at learning may be the kinds of things that tend to recur in the languages of the world. That is, that there might be a role for human learning abilities, and in particular, infant learning abilities is what I'm going to talk about, in shaping the structure of natural languages. So to try to make this argument, there aren't a lot of studies out there looking at how infants learn novel systems that are either like natural languages or unlike natural languages. And there really are very few studies out there that try to extend this to non-linguistic systems. So I'm going to present just two studies from my lab to try to make this point. The first example has to do with how babies learn about phonotactic regularities. Phonotactics are a really cool place to study learning because, so for those of you who don't know, phonotactics are regularities that are particular to specific languages in terms of which patterns of acceptability and positional restrictions on phonemes. So both restrictions about which phonemes can follow one another, but especially to do with position. So say at the beginning of a syllable versus the end of a syllable, there are different restrictions. In English, you can have F followed by S at the end of a syllable, but not at the beginning of a syllable, for example. And we know these differ from language to language, so they have to be learned. We also know that they're learned quite young, so by 9 months of age, infants can discriminate between words that show legal versus illegal patterns in their language. Moreover, they can discriminate between sequences that show probable legal versus improbable legal patterns in their language. So we know babies learn a lot about phonotactics pretty early. So what we wanted to ask is whether babies are better at learning phonotactic regularities that are more akin to natural languages versus those that are less akin to natural languages. And the way we did this was we designed a method that has 3 phases to it. In the first phase, babies hear a list of novel words that exemplify a particular set of phonotactic regularities. Then, instead of immediately testing them, they hear these words and they've heard these words in citation form. We then have the infants listen to fluent speech that has words that either are consistent with or inconsistent with the regularity that they've just been exposed to. And our question of interest is whether they are better at pulling out the novel words from the fluent speech that are consistent with the regularity that they've been listening to. So the idea here is that if they've learned the phonotactic regularity, they should devise expectations about possible word forms based on those regularities and have an easier time pulling them out of fluent speech. So in the first experiment, we exposed babies to a very simple list of words that follows a very simple regularity. These are all bisyllabic words. The two, I apologize, I don't have a laser pointer, so I'll just point like this. Maybe? Maybe not. Okay. On the far side, you have half the infants were exposed to the regularity on the far side, where each syllable starts with a voiceless consonant like t-k-p, t-k-p, and each syllable ends with a voiced consonant like d-g-b. The other half of the babies were exposed to the opposite pattern. Totally regular, totally predictable. And they listened to a list of these words for a couple minutes. And the question of interest is whether infants would learn the pattern they're exposed to, either the one on the left or the one on the right, and apply it to novel words that they're going to hear in fluent speech. So we're going to measure this possible newfound strategy to segment novel words as a function of what we expose them to during that first phase of the study. And the 4 words in our fluent speech, 2 of them are going to be consistent with the pattern the babies have heard, and 2 are inconsistent. So for example, for babies in the far side condition there, the novel word kib-pug is consistent with the phonotactic pattern they were exposed to, and boop-gok is inconsistent with the phonotactic pattern they were exposed to. Opposite pattern for the other half of the babies. And what we found in this first experiment was that infants were actually able to use what they learned about the phonotactic patterns to segment the novel words. And they discriminated between the items that were consistent with the pattern they heard at the beginning of the experiment versus words that were inconsistent with the pattern they heard at the beginning of the experiment. But how did they do it? Well, there are 2 possible kinds of information that babies could have learned in this task. One possibility, the way I wrote the phonotactic rule, has to do with voicing. So it has to do with a generalizable feature of the input, which is what seems to matter for the most part in phonological systems in natural languages. They care about generalizable patterns. But it's equally possible that what babies learned was restrictions on specific segments. So they could have learned, option 2 right here, which is that syllables have to start with t, k, or p, and they have to end with d, g, or b for the babies in that condition. And the study I've already shown you is equally consistent with both of those possibilities. So we wanted to ask, what do babies do? Were babies learning based on some generalizable type of feature representation, or were babies learning based on restrictions on particular segments? So we ran another experiment, which is very similar, except that we mixed around the phonemes so that now babies couldn't possibly learn by generalizing a phonetic feature, an acoustic feature, whatever you think voicing is. Don't have stake in that debate. They have to, if they're going to learn this, they have to learn it by memorizing or acquiring restrictions on specific segments, where d can go, where k can go, where p can go. But other than that, this experiment is identical to the previous one, and we have the exact same test items as well, same segmentation task and same test items. So if babies are able to learn this by tracking particular segments, they should do just the same as they did in the previous experiment. However, they fail to discriminate. So the infants did not show any evidence to us that they learned anything about the patterns that we gave them to learn when those patterns were written as restrictions over specific segments, as opposed to something generalizable about the acoustic or phonological structure of the input. These studies suggest that at least in this kind of, with the task demands of this particular input set, the infants learned when a generalization was possible, but they didn't learn when segment identity was critical, possibly because in the latter case there's more to keep track of. It seems representationally easier to have in your head some sort of expectation that has to do with where voicing goes, as opposed to some sort of expectation about where p goes, as opposed to d or t or b. So it seems possible that infants' propensity, the ease of generalizing here, might have something to do with why languages tend to have restrictions that have to do with categories of elements rather than individual exemplars of elements. And indeed, in a recent paper by Eric Thiessen, he demonstrates a very similar pattern of results in the visual domain, showing phonotactic learning, I have that in quotes, for shapes, for visual shapes, and showing that in generalizable contexts, infants learn more than in contexts where they have to track specific exemplar identity. Okay, so all patterns do not seem to be equally learnable by infants. And of course, at some level that's totally obvious. But it's interesting to try to ask which patterns are more learnable than others, and does that indicate anything interesting about, for example, why languages might be the way they are. The second learnability example is from the domain, I hesitate to call it syntax with all the linguists in the audience, but from the domain of, I'll call it phrase structure. And in walking through this, I profoundly apologize for the level of oversimplification of the syntax that I'm going to do to make my point. So I hope you accept my apology in advance. There's been interest since the late 60s, early 70s, in doing experiments to try to ask how it is that humans might learn something like linguistic phrase structure. Phrase structure is particularly interesting to people who are interested in learning because we might hear words serially one after the next, but our representations of them are anything but beads on the chain, as you all know. We have all expectations about which words and which categories of words clump together. And there's distributional information that might help learners to figure out which words clump together. These sorts of dependencies have been described since the structural linguistics of the first half of the 20th century. And the intuition is as follows. Certain types of words reliably predict the presence of other types of words within phrases. So, for example, you can have nouns without articles, but we don't have articles without nouns. We don't have sentences like the walk down the street in any language that I know of, unless the is unless the happens to be someone's name. Similarly, we can have noun phrases without prepositions, but prepositions require noun phrases somewhere downstream or upstream, depending on your language. We can have noun phrases without transitive verbs, but transitive verbs require object-noun phrases. These are all very obvious features of simple syntax. But in terms of the statistical manifestations on the surface, they provide the evidence of unidirectional strong conditional probabilities such that certain categories of elements reliably predict others, but it's unidirectional. Okay? So in work now done quite a long time ago, we wanted to ask whether these predictive dependencies buy anything for learners. Do they actually help us to learn? And so what we did was to create two artificial grammars that were very, very similar, and I'll give you their structures in a moment. The only real substantive difference being that one contained predictive dependencies such that certain word categories predicted others unidirectionally. The other lacked those dependencies. So I'll call this the predictive language versus the non-predictive language. Let me just give you the structure very briefly. This goes back to languages that were used in this like Bregman and Newport and Morgan in the 70s and 80s. These are very old languages that I've tweaked a little bit. So in the predictive language, let's just focus on the A phrase for a moment. An A phrase consists of an A word. A could be biff, sig, rud, or tiz, with an optional D word. And so the possible A phrases were A and AD. You can notice that this is a head final language, so it's unlike English, which is important because my subjects are American. Similarly, the C phrase can be written out with the rewrite rules as a C or a CG. You'll never have a G alone. So the presence of G tells you that C must also be there. Presence of D tells you that A must also be there. We'll contrast that with the non-predictive language. The non-predictive language is characterized by overarching optionality. So you can have an A word or a D word or both. The only criterion is you have to have one of them if you're going to have an A phrase. So we have actually multiple options for A phrases and C phrases that we don't have in the other language. So this would be like if in English our noun phrase rewrite rule was a noun phrase consists of an optional determiner and an optional noun, which is kind of weird. There's no dependency. There is structure. You still have to have an A phrase. You have to have one of these things there, but the language doesn't tell you which one. And what we did was to create two artificial languages, fairly large ones, where learners were going to be acquiring either a predictive or a non-predictive language. You can see from this simple comparison that in terms of surface structure, they were roughly comparable. And we started by testing adults and children on these languages. And what we found, using an auditory presentation, was that both adults and grade school children did better when exposed to language P than language N. The predictive language learners showed more acquisition of the structure of the language than the non-predictive language learners. Crucially, they had the same test. Everyone had the same test. All the items on the test were equally legal in both languages or illegal in both languages. And the test consisted of novel grammatical or ungrammatical items. Our next question was whether this was just about language, and it turned out that it's not. So here's stimuli from one of our experiments. So that was like biff, rud, lum, dup, sig, or something like that. We found with stimuli like these, we found the same pattern of performance with learners acquiring more about the predictive language structure than the non-predictive language structure. Here's another example of a language that we used. Oh, sorry. That's the same one. There we go. And you could argue in each of these, maybe people recoded it as language. We also used shapes. We did everything we could. And the same patterns kept reemerging in every case, except for when we use sequentially presented shapes. And that's a whole different talk. This work led us to ask, okay, for these learners who already know a language fluently, the predictive dependencies seem to help them, even though they're in the opposite direction of their native language. What would happen if we tested babies on these same materials, babies who arguably don't know much yet about syntax? And so we started by simplifying the languages substantially. I have how many minutes? 3 minutes. Okay. Babies learn this, but they only learn the predictive dependencies. They don't learn the non-predictive dependencies. How about that? Which is actually weird because this language seems really simple. We gave them the full language. This is the most complicated language that anyone has ever tested babies on, to my knowledge. And again, they learn the predictive language, but not the non-predictive language. Cotton-top tamarins, I won't go into that. Fine. Interestingly, Bengalese finches show the same pattern. They learn more about these predictive languages, the full predictive language, than the non-predictive language. So if these mechanisms are so general and seem to be available in a lot of domains, then what is it about humans and human language learners? And I'll end with some speculation. Part of what might be special about language learning and human language learners has to do with something that we don't see in a lot of other learning problems. And that is the following. When we're learning, we always have the same language, the same corpus. But as a function of learning, what we learn changes what we can learn next. So let's imagine that we're starting with sounds flowing over us. We don't know anything about words. Well, eventually, we're going to start to find those words, and then the words can become the input representations that get fed into learning. And then categories of words, and so on and so forth. One of the things that I think might be special about language and about creatures that can learn languages is that learning is a dynamic process. What you've learned at time t is going to affect what you can possibly learn at time t+1 in very deep and dramatic ways. And I don't have time to tell you about these studies, unfortunately, but we've done experiments in our lab showing that babies are able to go, for example, from fluent speech to word meaning, and that the output of one of those learning processes can serve as input to the next over the course of a single experiment. Or similarly, that infants can go from learning about word sequences to learning about the meanings of lexical categories, again, over a single learning bout, over a single learning experience. And so it could be that part of what is special, I apologize for having to skip all of this, but I can answer in the question period. What might be special about language learning is that you don't learn and then stop. It's not like your experiment ends. You're always learning. And what you've learned before is going to deeply change the way that the kinds of input representations that you're able to use for subsequent bouts of learning. So let me end by suggesting that we can talk about general learning without hopefully being accused of being flat earth empiricists. That learning mechanisms themselves, the computations might be domain general, but those learning mechanisms are embedded within systems that infants are trying to acquire, systems that have different forms of input and where the output can then become the input to subsequent learning. The constraints on this system are only, I think, just beginning to be understood. To use words from Simon Kirby's talk this morning, I don't know whether they are weak constraints or whether they're third-party stuff that's coming in there. But I think answering those questions could be extremely interesting. And finally, it may be something about the dynamics of being able to learn from one's own learning that might be part of what makes language and language learners so amazing. So thank you very much for your time. Before I end, would like to thank the people who actually did the work. and the people who paid for the work. And of course, we couldn't do any of this without the infants and their families, so we thank them greatly. Thank you.
Thank you very much. Could you use this one instead of that one?
Sure. Is it dying? Yeah. Okay.
And question, we have time, 10 minutes for questions and discussion.
Very nice. And it's been a while since I looked at this literature. So I wanted to ask the question of how well these mechanisms scale, right? So the work scientific stuff, which I'm more familiar with, we did some work and you know about it. And then there's also other work, more recent, I think, in speech learning literature, Johnson and Tyler and so on, showing there's some empirical conditions under which physical learning won't happen or won't be effective, and those happen to be the conditions that you see in natural language. I won't dwell on that. I wanted to talk a little more about this syntax part. This kind of predictive learning was tried in computational linguistics way back in the 1980s.
Excuse me, please make questions short.
Okay, I'm sorry. Okay.
Too long.
Okay, and they don't really work, which is why computational linguistics moved to parse corpora, so to do learning based on given the learner the target, right? So I want to hear your comments on the robustness of the physical learning, in particular for syntax.
I think my answer to that question, briefly, is that the claim here isn't about sufficiency. The claim is about getting the system rolling. And so if these sorts of mechanisms can allow infants to start to find the right pieces, begin to find the right pieces, even if it doesn't get them the whole way, then I think that would be very interesting. And the difficulty, I think, in both the word segmentation literature and the syntax literature is we can computationally specify how good some mechanism, how well some algorithm might do, but we don't really know how well babies do, right? And so I think as we get a better picture of the circumstances under which babies can and can't learn, then I think that's very helpful. In terms of scaling up, all of our work now in segmentation is done using natural languages like the Italian materials that I showed you, that you heard a little bit about, which are rich natural language input. So I'm feeling more confident about infants' abilities in that domain. In the syntax domain, I think the jury's willing to find out.
Thank you. What's this?
Well, beautiful talk. Thank you very much. I'm Nori Gosami from Kyoto University. And so it is out of your scope, but so the baby learning is a kind of a normal development. So, but actually there are some kids like autistic, and in that case, some of them can fluently speak or learn the word or grammar, but they sometimes don't understand the kind of the context of the kind of thing. So, and how can you comment on that? So, what kind of approach would be possible?
Yeah, we started to study different children with developmental disabilities. We have a published paper investigating these exact the kind of tasks in grade school children with specific language impairment. And it turns out that those children do more poorly on this task than children with typical development. Interestingly, though, they do the most poorly on the pitch version of the task. The is where the kids with specific language impairment really bomb, which is interesting and somewhat surprising. I haven't run the segmentation task on children with autism. There's one neuroimaging paper where people did, and they don't see the same signatures of learning that they see in typical children. we are about to start running some cross-situational word learning tasks on children with autism, which is a different kind of statistical learning task for word learning. It'll be very interesting to see what happens. So I'm extremely interested in different developmental trajectories with respect to these learning mechanisms.
Thank you very much for your informative talk. Kyoto University of Warsaw. I have a specific question, and it's related to the phonological distinctions that the children make. You use the consonants which have different bases of articulation, so you have labials, alveolars, and velars. And then, of course, those are begin to be produced at different times. And my question is, do you observe any regularities in some of those patterns being recognized more readily than the others? And then what the follow-up would be, do the children or babies conceptualize or categorize those sounds the same way as we as adults do so?
In terms of the phonotactic learning, we haven't specifically investigated, say, different places of articulation as a function of what's learned first. My intuition would be that production would not influence learning of these tasks solely because we see similar learning in tasks with sine wave tones and tasks with weird shapes. It doesn't seem to have either much to do with neuromotor production or even, dare I say it, the communicative value of what they're learning. In terms of whether they're learning in the same way as adults, those comparisons are extremely difficult to make. We've run many of these studies on adults, but our methods are very different. Adults, we can't flash lights and have them turn their heads. So we're now working on developing eye tracking methods that hopefully will allow us to equate the task demands more easily across infants and adults. Certainly ERPs are another way to do that. In the absence of equating task demands, I don't have a way to answer your question about comparability across age. I wish I did.
Jordan, can you hear me?
No.
Jordan from Kyoto University. A short and general question. Would you say that your results support the thesis of Evans and Levinson, the myth of linguistic universals? This paper is sometimes misunderstood as literally denying any kind of universals, but what they do deny are innate universals, but not the kind of things that one would expect to emerge from processes such as yours.
I had on my list of things to do is reread that paper before giving this talk, because I thought someone might ask that, and I didn't reread it. So I'm going to reread it tonight. Ask me tomorrow. I don't want to answer without rereading the paper, so thank you.
Hi, Rachel from Weekend BSI. The babies start with the ability to discriminate all those sounds, and then start losing, the ability to discriminate. Do you need a separate mechanisms to account for that than the learning system that you have?
Well, I think the studies by Luann Gherkin and Jessica May and Janet Worker have argued that tracking tokens of exemplars of phonemes will allow you to discover different types of distributions that can allow you to narrow in on your native language system. So as long as one extends the perceptual primitives to include exemplars of phonemes, and if one allows for tracking sort of histogram type structures, then I think in general it's quite a consistent perspective. There is, of course, Pat Poole's results suggesting that social interaction plays a really crucial role in that sort of narrowing of perceptual categories. And I would only say that in all of this learning, I believe that attention is crucial. We can show better learning, for example, when we use infant-directed speech in our materials than when we use adult-directed speech. And so I think that there is an attentional gating that might have something to do with that social interaction as well.
Irene Pepperberg, Harvard University. I have to ask you about the non-human, obviously. When you say using knowledge to gain more knowledge, would you consider when an animal can segment English speech and then use that knowledge to form new labels based on phonemes it already knows?
I would if there's evidence that the training had been in fluent speech and not single word, repeated sort of exemplars. In fact, the study I had to jump over was exactly that with babies, giving them exposure to fluent speech and then seeing if they could map statistically good words as labels. If we could show that in a non-human, or if you could show that in a non-human, I would be very compelled. But I would be less compelled if I was hearing words in previously segmented speech.
Thank you very much.